Hi, and hello everyone. Welcome back to our third session of the CCP-EM Spring Symposium. Still a few more people filtering in from lunch, but I think we'd better get started, or we'll be here all afternoon. So we'll get started on this session, which is themed around method developments in electron cryotomography. And kicking us off are going to be Éilís and Chris from EBIC and Diamond Light Source, who have changed their title from what's in the program to make it more, to include more wordplay, I think is the idea. But they're going to be telling us about some exciting developments with lasers and cryo-FIB.
Thanks, Colin. Yeah, I can't take credit for the talk title. That's all Chris. Thank you to the speakers for inviting us to speak today. To the organizer, sorry, for inviting us to speak today. So we're going to present a novel workflow for preparing lamella from waffle grids for cryo-T. So just to give a bit of an overview, so for standard workflow for cryo-FIB SEM experiments is you will either grow or deposit your cells on grids, plunge freeze them, mill them, carry out FIB milling, and then move on to cryo-ET. So what does a standard cryo-FIB look like? So here's the example here of, we've got laser one time, cool, of the aqualoss at EBIC. So you have a electron beam and an ion beam source, and will the video play? I need to turn the laser page on. Sorry, trying to get the video to play. There you go. Yeah, so this is what a grid generally looks like with cells which have been either deposited or grown. This is then, you then use the ion beam to remove material either side of the cell so that you end up with your nice thin lamella, which are then transparent enough so that you can see all your nice cellular features inside the TEM. Okay. So the limitation of sort of the standard plunge freezing or workflow for this is you're limited to sample thicknesses of about 10 microns for your cells. So about 4 years ago, the waffle method was sort of introduced. So as an alternative method, you high pressure freeze your samples rather than plunge freezing. So this means that you can freeze cellular slurries with more densely packed cells, and this is great for things like bacteria or small single cellular organisms, because you can get a lot more bang for your buck inside your lamella. So the general workflow for this is that you take your two planchettes, apply your sample to your cryo-EM grid, high pressure freeze, and then move on to the milling. So to begin to generate your lamella, you need to do, it's known as pre-trenching. So you need to clear material either side so that you end up with this block in the middle. And this is generally done manually. There's no automation as of yet for this process. And then for general lamella stability, you then introduce, it's known as a notch, to sort of break away from the main bulk of the material so that then when you start thinning your samples, you're not putting too much stress on your lamella. And then from this point, in most softwares, you can actually automate this process. But also another thing that we need to take into account is that to actually get to the point where you can see the bottom and clearance in this step for generating your if we can start generating lamella, you actually have to do multiple clearance steps at different milling angles. So this process takes a fair bit of time. So there's many benefits to the waffle method. So it gives you the ability to freeze sort of more fussy cells which are not as amenable to growing on grids, or sometimes you can actually have disrupted biology through plunge freezing. And because you end up with these much thicker, because you can get these thicker samples, and you can actually get your cells in multiple orientations, which means that you can suddenly start accessing biology, which you may not have been able to when it's just when your cells run a planar field of view. You also get these bigger lamellas you can see here in the image, which means that you should end up with higher throughput cryo-ET through the workflow. And it also requires less specialized hardware and expertise than cryo lift out because it's still an on-grid milling method. But as I've said, the limitation is still slow. It's still slow, so it can take a fair bit of time to generate like the pre-trench slides to begin with, and then to actually generate and to get your lamella at the end. So what can we do to negate this? And I'm going to hand over to Chris to explain what we can do.
Okay, thank you very much. So the solution, most of my solutions will involve lasers. And the specific laser system that we've built here, we are calling the I-23 laser shaping system. This was originally built for laser shaping protein crystals into spheres for a completely different set of experiments. But essentially, we can use the same setup for multiple different things. So this is what the setup looks like in real life. It's not as clean as the image before, but you have things like a cryojet to be able to work under cryogenic conditions. Galvano scan head, this is where the laser is actually coming out. Femtosecond laser, this is the kind of core of the whole piece of equipment. A goniometer, which is very widely used in MX for orienting samples in the beam, and a cryo-compatible robot arm for quick sample exchange. Additionally, we also have this 80 sample capacity dewar, which means that we can get quite a lot of throughput. So when I say we've used this, we've made this laser for one case, we've used it for things like cutting chemical crystals, volcanic rocks, clays, and kind of sapphire discs. Anything you can think of, we've had a go at cutting through. The special thing about this laser is that it's a femtosecond laser. So a traditional laser that would be used for cutting things would be a continuous wave laser. Think of these big cabinet lasers that you have. They're normally kind of 60-watt infrared lasers. There is a system that does cutting of biological material that is based on deep UV, so it targets the protein-protein bonds. We have gone with a different kind of technique, different technology, which is this femtosecond laser. So what we're doing here is we are exploiting the multi-photon effect. The way this kind of works is that you have your electrons in the ground state, and you bump them up with a photon, and before they have time to fall back down again, another photon comes back in. This is because we squeeze all of our light pulses, all of our photons, into a very, very short frame of time. So 2 times 10 to the minus 13 seconds. What this actually looks like, so this is what a continuous wave laser would look like, and here's a femtosecond laser. You can see that the actual laser part of it, the thing that you can see, is much more controlled. It's a very, very small beam, and you don't have all of this burning that would happen in the cone before and afterwards. So I lied to you a second ago a little bit. It's not just this multi-photon effect. There's also this second way that it's cutting, which is it's called tunneling ionization. So here, the electric field that you generate with the laser, because it's such a large amount of photons in such a small space, in such a small frame of time, it changes the binding potential of the electrons, and it means that they can kind of quantum tunnel out the side of this bent barrier. Either way, the electrons leave, and you get this it's a Coulomb explosion. So the atom actually just vaporizes, stops existing. This is useful for cutting very delicate things like biological samples. You have an extremely low thermal component here, a very low power. So we're using just a 3-watt laser here. It can cut through literally anything. We haven't found something it can't cut through yet. And it's very localized. Our full width half max on this is 5.8 microns. But again, this kind of multi-photon effect only happens right in the center of that, where you're satisfying the temporal, like time and space of all of these photons being in the same place. So we had to do a little bit of playing around with how you load these samples. It's, as I said, it was built for protein crystals, but now we're adapting it to EM grids. A lot of the things here you will probably recognize and have some free advertising for sub-angstrom as well. And the things that you might not have are these. These are very, very common in MX labs. They're probably looking to throw them away because we use smaller ones now. And then the things that we developed were a interface between the goniometer and the grids. So these are heart surgery clips that I've glued into spine mounts. And here's how you load them in. So these pucks hold 16 in one go, and we can fit 5 pucks into the robot dewar, so you can get 80 of the grids in there in one go. What this actually looks like, so this should be a video of the robot putting a grid or taking one off of the goniometer and putting one back in. We're keeping it cold with the nitrogen stream the entire time. And then here's a close-up view of what it looks like. You can see the grid being held in the cryo stream. This is where the laser comes out of, and this is the box with the mirrors that steer the lasers. And we also have this high magnification microscope if you're not able to see what you want to see. And you can kind of see me orienting it in the beam here. I will skip to the next bit. We are generating these free lamella, is what we're calling them. So on the left-hand side, this is the trench, and this part in the middle is the bit that you leave. We also have the option to cut this notch out at the side, like Éilís explained earlier. And really, the measurements that I've put on the side here, this is what we've used to show you things here today, but you can make whatever shape you want. If you can draw it, then you can cut it. The first thing that we do is we cut a big triangle in the bottom of the grid. This makes it very, very easy for you to find where things are when you're moving things from a FIB into a TEM. And then the next thing that we do is we get everything nice and in focus. So I've put the first bit of the video in 1x speed. And what we're going to do is just clear through kind of 10 trenches in a single pass. And then afterwards, I'm not going to make you watch me do the whole grid. I speed it up 5 times and do the rest of the grid. So you can see here, you get a load of nice pre-lamella there. We have an added benefit that we don't really know why it's happening, but it completely gets rid of the ice. So some of these bits here, you would go, oh, I'm not going to cut through that because it's just a load of ice, but this thing just kind of blasts that out the way. So you can see a full grid being made here. This entire video is 6 minutes from start to finish. And then you don't have to do it that way. You can do single points. And here you actually get this layer in the middle. So your lamellas are here with the notch cut, but you actually get for free in the middle of them another layer of lamella without the notch. And you don't have to put the notch in either. This is one without the notch. But the other thing is that we can speed this up even further, and this is in real time. So that video on the right-hand side is 0.8 seconds to get one of these cuts done. Overall, what does the workflow look like? So you do your cell culture, your high pressure freezing, and then what you would normally do is you take it to a FIB or to an Arctis or an Aclos. That's what we've used here. And overall, we estimate that the kind of trench mapping is finding the places you want to put these things and starting it off, and then it's 20 minutes on an Aclos, 4 minutes on an Arctis. Then you would put it through to the milling and polishing step. We basically take away these 3 parts, which are very manual anyway, and we replace them with this bit at the top. So it's an 80 grid capacity that you can get through, 4.5 seconds to center and kind of orient your I was about to say crystal grid. And then trenching takes just 4 seconds or 0.8 if you're ambitious. And then you would transfer it to the FIB and do your milling and polishing. So after 1 puck, the overhead of actually cooling all these things down and transferring it to this other instrument are kind of gone. With 1 grid, you can get 80 lamella, roughly, 80 pre-lamella, and that's a 27 times speed up on a P-FIB and a 91 times speed up on a gallium FIB. But where it really becomes interesting is if you fill that dewar full of grids, you can get a 195 times speed up on a gallium FIB or a kind of 57 times speed up there. The even more interesting thing here is that this number is about 13 hours. And this number is more lamella than you're probably ever going to be able to look at. And like Éilís said earlier, they're quite big lamella when you polish them. So you can get about 20 tomogram sites per lamella, and that's 128,000 potential tomogram sites, which is, I think we worked out, it's more than 1 year of cryos time. So back over to Éilís for the results.
Yeah, so as I said, saw the isomelon principle, that does it actually work and can you get cryo-ET data out of it? So Chris has already shown you, like with the videos and things like that. Sorry, this is quite dark. So we're going to show you the workflow, which is completely automated, where we've actually put the already pre-put the cut in. So this means that effectively you can load. So this is an example from the Aqualos where you can load straight into the FIB, and actually there should be no manual milling necessary. So you can map, find your lamella positions pretty obviously, and then set up, and you can leave it automated and running overnight. So then we end up with the clearance going through here, clearing the top and bottom. And you end up, we go with these sort of lamellas just sticking out the side, which are nicely thinned and ready to then go through for your cryo-ET workflows. So here is an example of some subtomogram averaging that we carried out on lamella, which were generated first with the pre-lamella, were generated with the laser, and then thinned with the Arctis and subtomogram, and then went through, collected all our tomograms and did the subtomogram averaging. So we've got an overall, like a global resolution of about 6 angstroms, I think, over this. So yeah, it's just showing that we can effectively get actually get experimental data out of this method. So just to summarize what both Chris and I have shown, is that we've developed an open source method which significantly increases throughput of lamella sites, which you can generate on waffle grids. So we've tested this on an Aqualos and an Arctis, but we think there's no reason this isn't going to be compatible with any other cryo-FIB setup. And the lamella that we generate produce quality tomograms, and it's amenable to high resolution subtomogram averaging. So hopefully you can get your results quicker by using this method. So as much as it's been Chris and I have presented today, it is a group of us, and then in a great collaboration with the University of Oxford. And we also do have a poster in the current session. So if you want to come and look at that, you have some time in the coffee break. And yes, so that's it, and welcome any questions.
Thank you very much, Éilís and Chris. I always particularly enjoy the combination of high and low tech hardware that is always involved in these kind of projects.